Welcome back. Hope you're doing well. Last time we discussed eigenvalues and eigenvectors in a real space and came up lacking with some particular operators in determining whether or not they would be diagonalizable. The issue with some of these was multiple fold, one of which was sometimes you just have a real eigenvalue, but there are not enough eigenvectors to fill up your eigenspace. Essentially, not enough in order to make a basis of eigenvectors from there. But sometimes, on the other hand, you have eigenvectors that or eigenvalues that are imaginary in nature, right? For example, whenever you have let's say a characteristic polynomial that is of degree 2, you could have something that just does not have any real values, much like lambda squared plus 1. If you do this, then in the real numbers, you're out of luck because there are no values of lambda that can help us work with this. But what about some of these operators that end up being diagonalizable in a different space? What if these end up being diagonalizable in terms of the complex numbers? In this video, we'll talk a little bit about eigenvalues and eigenvectors when considering things as complex vector fields getting potentially complex eigenvalues, and try and move on from there. So first things first, fundamental theorem of algebra says if we work in the complex numbers, we do a lot better on this front. Namely, you're not going to have an n-degree polynomial and have fewer than n complex roots even. You're going to have exactly n roots when counting with multiplicities. So that statement is the fundamental theorem of algebra, that if you have complex coefficients for your polynomial, so an minus 1, a1, a0, so something of degree n, then you get exactly n roots once you go through and factor it. You're going to get to be able to write that polynomial in this particular form. Here, z1, z2, and zn are our roots for this equation, and these are complex numbers now. Now, this isn't to say that this formula doesn't allow us to get n roots if everything ends up being real coefficients. In some cases, you do have that. We've seen lambda squared minus 2 lambda plus 1 factor out to be lambda minus 1 quantity squared. And that is just one real root, but with multiplicity 2. That's exactly what this sort of theorem is talking about. It's okay for some of these to repeat. It just can be factored into this form. And 1, by the way, is a complex number. And remember that the way that we write complex numbers are in the form a plus bi. So 1 is just the number 1 plus 0i. So the real numbers are included in the complex numbers whenever we discuss them in this form. So let's take a look at this in terms of the example that we've been looking at before. The example a equals 0, negative 1, 1, 0. Let's go through and calculate this characteristic polynomial together now that we know we have eigenvalues that can be complex. So here we have a little bit of the work. We'll come back and detail this in just a little bit. Let's go through and do this work ourselves. Here we've got a equals 0, negative 1, 1, 0 as our matrix, and we'd like to go through and find eigenvalues and eigenvectors. Let's call it eigenstuff. So we're going to have a minus lambda I to help us generate our characteristic polynomial. So we're going to have minus lambda on each of our diagonal entries. And going through and finding the determinant of this is going to give us something like this. We're going to have what? Lambda squared for multiplying the diagonal. And then we're going to have minus negative 1. That's going to give us plus 1. Well, this is something that we want to be equal to 0. So if we're in the real numbers, again, we're done. Lambda squared must be greater than or equal to 0. Adding 1 is going to get us something greater than or equal to 1. In particular, it'll never equal 0. But in terms of the imaginary numbers, that is not true. We've got that lambda squared equals negative 1. So lambda equals plus or minus I until we go through and take square roots of both of these, getting both of these values. So now that tells us that we have two eigenvalues. By the way, those same sorts of theorems are going to be useful for us here because now we have two eigenvalues in a 2 by 2 matrix. Let's keep that in mind as we go through this. So first things first, let's actually try and find eigenvectors for each of these. Let's try to find an eigenvector for lambda equals I. So if we're going to do this, we're going to be plugging an I in for lambda, and we would like to try and solve the equation. Negative I, negative 1, 1, negative I, and then some vector, we can call it x and y, equals the 0 vector, 0, 0. So we can now go through and calculate things based off of this and see what we're able to get here. And we can do this in any number of ways. We can use the matrix Gauss-Jordan elimination. We can just try and figure out if x and y are easy to get here. I'm trying to look through and see which one I'd like to take. I think I'm going to go ahead and use Gauss-Jordan elimination. So something like this. 1, negative I, and 0. And let's see what we're able to get. Well, I would like to eliminate 1 from this equation. Okay, so maybe what I can do is multiply this top equation by negative I up on top, and then add that to this equation right down here. Let's see what that's going to give me. Negative I times negative I, by the way, is the negatives cancel each other out. So I just have I times I, that's going to be negative 1. So 1 plus negative 1 is going to give me 0. And then negative 1 times negative I is just going to give me I. The negatives cancel each other out. So I'm going to have negative I plus I. That's going to give me a 0 down here. So I get negative I minus 1, 0 as my matrix after going through and doing all of that. Notice I have my 0 row. That's exactly what I would have expected. So I'm going to have negative I times x1 minus x2 equals 0 for my equation of relating these two things together. In particular, I could solve for x2 here and get that x2 is equal to negative I times x1. So this is our way of writing how this sort of thing works. Namely, if I want to get an eigenvector for this, I could just plug in x1 equals 1 and gets that the eigenvector is 1 and negative I. Notice that my eigenvectors also have complex numbers inside of them. 1, negative I is my eigenvector here associated to my eigenvalue of I. And then we could go through and do the same thing, but this time for lambda equals negative I to get our other eigenvector, and then we could write things out that way. Now the question is, does that theorem that we were talking about before, namely I have n distinct roots for an n by n matrix here, so I have 2 roots here. Each one has an eigenspace of 1, as we can see from our work up here. We've got associated eigenvectors of this and this for each of our characteristic roots. Is it true still that this is a basis of eigenvectors? The answer is yes, but it's not in the way that you would think. Think this way. Right now, we've got essentially 2 complex numbers going on. We've got the complex number in the first component of our vectors inside of our space, and then we've got the complex numbers going on down in here. Now, we've got 2 copies of complex numbers here. So how do we mean when we say that something is going to span to be a basis? Because I thought the complex numbers looked a little bit like R2. If you haven't seen this before, let's draw this out. The complex numbers, at least algebraically speaking, in terms of everything except for multiplying matrices in terms of themselves, so in vector space notation, C is equal to R2, right? So these two things should be thought of as very similar to each other, the complex numbers and R2. So pictorially, what we're doing here is we're saying this is kind of like our real axis down here, and then this is our imaginary axis down here. So the vertical axis is now an imaginary axis. So if I have a number like 3 and I want to multiply it times I, what I'm doing is I am essentially multiplying it by rotating it around by 90 degrees. Very interesting because our matrix before was rotating by 90 degrees, that time with respect to the x and y axis, not with respect to this one, right? But I digress. So these are our 2 axes here for working in terms of the complex numbers. So how is it that I mean that these 2 vectors are a basis here? In which space are these a basis? We'll take a look at where these scalars are from. These scalars are not from the real numbers. Remember in our very first videos from this class, we said most of the time the real numbers would be our vector space, or rather our scalar field, over which we would have a vector space over R. But these, you can see, are scalars over C. These are scalars over the complex numbers. Well, if C is equal to R2, this is kind of like thinking of R2 as being as C2 being a vector space over C. Or if I'd like to write it like this, here's a copy of C2, which is very similar to R4, is like playing it like a vector space over R2. Now, if I'm going to write this, I'm probably going to talk about complex numbers squared rather than real numbers to the 4th, just because it's a little bit more clear what I'm talking about. But the reason that I'm wanting to emphasize here, R to the 4 here, is that I have a lot of degrees of freedom here, right? This is 1 plus 0i and 0 minus 1i. These numbers are all different numbers that I could have access to, each one a copy of the real numbers. I could put a real number here, 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 and here whenever I'm talking about a vector inside of C2. So how many real numbers is that? That's 1, 2, 3, 4. That's R4. Hence why we talk about C2 as being very similar to R4 whenever we discuss it. And also why we consider the real numbers or the complex numbers themselves to be a lot like R2. So V1 and V2 is a basis of eigenvectors, but over the complex numbers, over C, it is a basis of eigenvectors. So it is not over the real numbers. In fact, you would see here, we don't have enough for the real numbers. We'd be looking at R4 if we had this as a vector field over the real numbers. So we would need 4 eigenvectors to make that work. Well, we only have 2. The reason that it's okay to have 2 eigenvectors, this one and this one, is that we have C2 and that this is a vector field over, or a vector space over C. So that ends up being a little bit important to us. If this was over R, we'd be looking at this like R4, and we need 4 eigenvectors instead. But instead, this is a vector space or a basis over C for this operator. Now, talking about this space a little bit more, because sometimes it's been a while since we've seen things, how they work, how in the complex numbers. Let's talk about that multiplying times I business that I did again. One way that I can think about elements in the complex numbers is as R2 vectors, very much like this one is here. This would correspond to the complex number 1 plus I. In fact, if I wanted to write it a little bit differently, maybe I could even write it like this and say that everything in the first column element is real and everything in the second column element is imaginary. So it's the coefficients 1 and 1, 1 being real and 1 being imaginary. So 1 plus 1I. Well, what happens when I multiply times I? Well, and I multiply times I, I'm going to get I minus 1, am I not? Well, those two things are going to flip places in terms of how my vector is situated. So this is going to be negative 1 plus I, or if I write that in terms of my vector notation, negative 1 and 1. Notice that that is a 90-degree rotation there. This comes back to our discussion of this very operator we were discussing before. This is a rotation of 90 degrees, but not in terms of the R2 plane. This is in terms of the complex plane, in terms of this being R and this being R times I. So in general, how would I write this algebraically is a good question. So if I want to say I am multiplying, I'm looking at the map of multiplying X times a number I. Another way to think about this is in terms of the following. Well, we know that what we're doing is we are multiplying, basically we're taking A plus BI, and we are replacing this with, in this case, something like, this is from 90 degrees. This is going to be for negative B plus AI, right? Well, this ends up being the same thing as if I took this number and I had it as multiplying times the following. Cosine of pi over 2 plus I times sine of pi over 2. Depending on your exposure to the real numbers, this might be something familiar to you. This is the operator known as rotation by 90 degrees, or better to say, rotation by pi over 2. In general, I could replace pi over 2 with theta and also get a rotation by theta, but it would be rotation by theta in terms of the complex plane here. So if I were to multiply a plus bi times this, remember cosine pi over 2 is 0 plus I times sine of pi over 2 is 1. This would be the same as multiplying times I. The reason that I write this is that another way for us to write cosine plus I sine is e to the power of I times the following power, whatever power it is that we have inside of here. That power here is going to be pi over 2. So these two things are equal to each other. So I could think of this as an operator taking the complex numbers, z from C, going and mapping them to z times e to the I times pi over 2, also in the complex numbers. So this is a linear operator that corresponds to rotation by 90 degrees inside of the complex plane. If this is a little bit weird to you, like why are cosine and sine popping up here, which I think is a good question. Why are cosine and sine popping up here? You remember that one video that we talked about and when we discussed how rotation by an angle ends up having a matrix of rotation given something like this? Cosine of theta minus sine of theta, and then sine of theta cosine. The answer is that there's a lot of similarities between that and this part of rotation that we're doing here. Cosine pi over 2, sine pi over 2, that stuff just plays the same role essentially as what we're trying to do here. So maybe that will help make this connection here by looking back and reviewing that sort of content for this particular component. But what we're doing is we are, instead of working with the real numbers, we are complexifying. Instead of the real vector space R2, right, working in terms of vectors that have just x and y inside of them, we have been considering the complex vector space a plus bi and c plus di, just when all complex numbers are admissible as scalars as well. So they are vector spaces over C rather than over R. So the linear operator, taking from r squared to r squared, f of x equals ax, where a is like our example from before. It's been a while, so I'll make sure to repeat it. Here is that matrix A. We can extend this operator, R2 to R2, to be a complex linear operator going from C2 to C2. What is this? What we're doing is we're saying, okay, we know what this looks like on R2. We know what this looks like on the XY plane. What does this look like on C2? What if on each real axis we allowed our real numbers to become complex numbers? Well, each real axis becomes a copy of C2. So really you get 2 copies of C2 and X, and then 2 copies of C2 and Y. That's going to give you 4 total copies of the real numbers. So if you want to think of it, it's like kind of like R4, R4. But of course, we're trying to think and retain the notion of complex numbers here. So we write C2 to C2 for this operator being exactly the same. A is still the operator, 0, -1, 1, 0. But now we're allowing ourselves to multiply times complex vectors, vectors with complex numbers inside of them. So now these vectors form a basis of C2, a dimension 2 over C, and with 2 vectors inside of them. This is the notation. This is the stuff that we were talking a bit about before, that C2 is also a real vector space, meaning it has real dimension 4. Namely, if you look at this as R4, it's got 4 components that you can put in for it. The standard real basis for C2 is given as below, 1, 0, 0, 1, standard basis for R2, and then the same thing for I0 and 0, 1. The matrix of the operator F given up here, if we were to look at this as a real basis, would look a little bit like this. A times for the real numbers and then A times for the complex numbers. That is the sort of log structure that we would be getting here. All right, so this is the sort of thing that we have when we're discussing this sort of stuff. But the big thing to take away here is that the complex numbers can have us working with more eigenvectors than we had before. So complexifying a vector space can allow us to get to diagonal operators sometimes where we could not. Now, this is not every single diagonal operator. We still haven't dealt with the case that sometimes your eigenspaces just don't have enough space for enough eigenvectors. That still can exist even in the complex numbers. But at least now we don't have the issue of eigenvalues not being real. If we complexify our operators, we can now look at this as having a basis of eigenvectors over C rather than over R. Well, that will do it for today. Thank you so much. Have a wonderful day.